So this was a hypothesis. This is the proposed low energy effective action for the condensate. It's not something that is, how shall I say it? It's not something that was mathematically derived from the original action in a direct sense. Rather, it came from the expectation that the interactions of what goes on here generate this via some physics we don't entirely understand, but we'll say once we've got this, what is the right way to describe the physics of this structure here? And so they say, well, the simplest thing we can write down is that this is just the derivative of the condensate. I mean, if you look at the definition, this is just the derivative of the condensate times the derivative of the dagger of the condensate. That's all it is. So the idea is the condensate is the kinetic energy of the condensate. So how do these condensates interact with each other? Well, to leading order, we're not going to put in interactions until we understand the leading order. So you could do that. But one of the interactions that had to happen comes from this. Then you might imagine you want to put others in theory. But it turned out this was remarkably, forgetting about the anomaly, this was remarkably effective for describing kaons, pions, eta mesons, rho mesons. All of these different mesons and their varying decays were very well described by this simple thing. But there were a few things that did not work. One was pi and 2 photons, which was why they used this. So that's where that came from. It's not a renormalizable Lagrangian. But that doesn't matter because the idea is it's a low energy effective Lagrangian. So when you go to high energies, the condensate dissolves and the actual I'll write it over here. It's hard to see, sorry. Pi is defined as 1 over twice f pi times this condensate dotted into the gauge field center. That's all that pi is. It's a common notation, yeah. Well, it is. I mean, we did that. If you look at what the pions do, in some sense, that's what we did. Whatever was Monday of this week, I think, or Tuesday, I forget. But so it is. But the point is to generate this without worrying about those triangles. See, the quarks have all disappeared in this formulation. The mesons are all either pseudo-scalar fields or pseudo-vector fields or something like that. So the idea is, can you describe those interactions without going back down to the quark level? And the answer is, yeah, that term doesn't. That's the point. So you could. In fact, that's what people did. And so that's the connection. Does that make sense? Basically, yes, that's right. At the condensate level, that's correct. The idea is the quark terms just get wiped out entirely. The mesons have no idea they're made of quarks. They behave according to that effective action with that other term. And this works very well, actually, to describe low-energy meson physics. In fact, it works better, I think, than people thought it ought to when they constructed it. So the idea of that was to show you, it was to follow up on what that X gamma stuff does. It's used in generating, it can be used in generating effective actions, and partly, I guess, still is used if you're a person who believes that there is substructure to quarks or leptons or what have you, then similar ideas would be used, that an electron is the condensate of, I don't know what, preons or retons or something. Those ideas were used there as well. To my knowledge, there is no positive evidence to support these kinds of substructure models, and people don't work on them anymore, or hardly anybody works on them anymore for that reason. And the favored substructure model, if you can call that, would be something like string at this point. Yeah. Pardon me? I don't know why you use the word maybe gray matter. What do you mean? I mean...